All right, everybody, here is our video on mass energy equivalence. Okay, mass energy equivalence. This is kind of a weird thing to think about, and it kind of defies everything that we've done so far. Um, However, this really does introduce you to one of the biggest topics that you have heard about, but you probably have no idea what it means yet. The premise of this comes from, right, let's say we take a block, and then maybe this block is 4 kilograms. Maybe I split this block into two pieces. Maybe I split it into two blocks of 2 kilograms each, right? Maybe I split one of those blocks into a 1 kilogram and a 1 kilogram, on and on, whatever it is. When we do this with particles, let's say I have some particles that decay and decay and decay. What ends up happening is this really weird phenomenon where the masses at the end, right? That's what we have at the masses at the end. We expect them, just like these blocks, to add up to what we started with. But what we end up seeing is that that's not true when this happens with particles. Take, for example, here's one of the reactions that was first used to look at this whole mass energy equivalence. This is essentially this is what happens in the sun to give us light. This is part of the process. This should be a 2 right there. This is part of the process that happens in the sun why we have light. This is the fusion of a couple of hydrogen atoms, and it took a couple of hydrogens to get to this point. Over here, but we'll forget those steps right now and just look at this reaction right here. So we have hydrogen with a mass of 2 plus hydrogen with a mass of 3. Those combine to form helium nucleus, right? 2, 4, and 1 neutron because we have to balance, right, the nucleon number. What we get when all this happens, what we get is we have this 2.0135553 U. This is just we've measured the mass of what these things mean. This U right here is a unit of mass. If you look at your AP equation sheet, I'll flip over there real fast. This U, we can see this right here, one unified atomic mass unit. It gives us what a U is in terms of kilograms. You'll notice that that is very, very, very close to what a proton is in kilograms and a neutron. It's very, very close. What it truly is they took carbon 12 and then divided that number by 12. That's how they got one U. But for now, all you need to know is that's a unit of mass. All three of these are units of mass, and we'll talk through those shortly. And there's your conversion factor between all three of them. So we have that much mass from this hydrogen mass of 2, the hydrogen mass of 3, and I'm pulling all these numbers. I've looked up this reaction. I definitely don't have this memorized. Has a mass of that. But then when those two combine, they form this mass of 4.00, this is for the helium, 1506, and then this neutron, 1.008665. These are all in units of U. I'm going to see if my calculator pulls up. It's been giving me some problems here recently. So let's see. Nope, still giving me problems. Okay. So I'll grab out my own real calculator here. Feel free to follow along with these calculations as I am as well. Sorry, I'm setting the backpack down. Okay. But on the left side, right, our reactants for this, if I take 2.013553 plus 3.016049, I get 5.029602 is what we start with. But on the right side, when I do this same process, I get 5.010171. So somewhere there was some mass lost, which is weird. And that mass lost is actually 0.019431 U's. But somewhere, this amount of mass just disappeared. It's just gone. What we do now, and this was an Einstein solution, which is actually kind of cool, is Einstein said, okay, everything we've done in classical physics, well, at that time, they just called it physics, but this conservation of mass, all right, that's probably something that you've heard. I'd be honestly shocked if it wasn't. But conservation of mass, Einstein said, how about no? There's no such thing as conservation of mass. Einstein said, instead, what if we look at this in terms of conservation of energy? So we don't have this conservation of mass anymore. We have essentially that would turn into conservation of energy. And I would be even more shocked as before if you had not heard of his equation to relate these: E equals mc squared. Einstein came up with this simple equation to say that energy and mass, and he calls it the mass-energy equivalence, which is why that's the title of this video. Energy and mass are related simply by saying E equals mc squared. So the amount of mass that you have, take it and multiply that by the speed of light squared, and that's how much energy it would just turn into. So if we look at this equation or this example up here, how much energy would this reaction release? Right? So this is fusion, right? We're taking two small nuclei and turning it into a bigger nuclei. So this is fusion, and fusion produces energy. That's what gives us the sun's light. So if this didn't produce energy, we wouldn't exist. Nothing in the solar system would be visible whatsoever. But how much is that? Well, we have this equation, E equals mc squared. E equals mc squared. I'll give you a hint. There's two useful ways to do this. One, we could do energy in joules, mass in kilograms, speed of light in meters per second. That's one useful way to do that. Or, all right, if we take a look at our equation sheet, we just did mass in kilograms is what we just talked through. But there's two other units of mass. We have this U here, this atomic mass unit, which is basically, it's very similar to a proton. Or we have this unit of MeV per c squared. This is a really weird unit here, MeV per c squared. That is mega electron volts per the speed of light squared. Mega electron volts per the speed of light squared. What that means, one atomic mass unit is equal to 931 mega electron volts. So, right, that's times 10 to the sixth. That's mega times 10 to the sixth electron volts. Over c squared, over the speed of light squared. So the other way we can look at this is in terms of electron volts is equal to, and actually I should say, well, make the pen a little smaller here. I should say mega electron volts is equal to our mass in terms of MeVs per c squared, mega electron volts per c squared. Because, right, that's mass times, and then what are we going to do for the speed of light? What units? Well, it actually doesn't matter. We just say per c squared, and then that goes away, and that goes away. So this tells us that our energy in terms of mega electron volts, or times 10 to the 6 electron volts, is just equal to however much mass there is in terms of this unit of mass, MeV per c squared. It's really kind of weird. But we can do this. Let's try this out in both ways. So 0.09019,431 U's, if we were to take that and turn that into joules, um, I'll use my orange for joules like I was just doing. Right, here we go. 1 U is equal to 1.66 times 10 to the 27 kilograms. So I just take however many U's there are and multiply it by 1.66 times 10 to the minus 27. That gets us in kilograms. So we have some amount of energy. Our mass, we get 3.23 times 10 to the minus 29 kilograms. All right, speed of light is 3 times 10 to the 8th, and that gets squared. So the amount of energy released that we have, if we take those two answers, multiply them together, so times 3 e to the 8th squared, I get 2.9 times 10 to the minus 12 joules. Okay. And now let's try this in terms of, I don't really know why I drew these arrows, but here we go. Let's put this in terms of MeV per C squared. Well, so if I take this, and that means, right, our energy is our mass, and our mass, 1 U is equal to 931 MeVs per C squared. So 1U, so all I have to do is multiply, here we go, multiply this number, multiply this 0.019431 times 931, and that gives me 18.1 MeVs, mega electron volts per C squared. So E equals mc squared. Well, what's great, there's speed of light squared on top and on bottom. Those cancel out. So our energy is actually just equal to 18.1 mega electron volts, or times 10 to the 6 electron volts. Okay. Well, what's really cool is you can actually see that these two numbers are equivalent, right? Because back to the equation sheet, we have, where did it go? Up top here, 1 electron volt is equal to 1.6 times 10 to the 19, 10 to the minus 19 joules. So if we take our energy in terms of electron volts, this 18.1 times 10 to the minus, or times 10 to the 6 electron volts, we take that times 1.6 times 10 to the minus 19, I get 2.9 times 10 to the minus 12 joules. There we go. So these are the same answer. Whichever one of these you pull out is the same answer. They're equivalent. It just depends how AP asks you the question. Okay. So, right, we've got mass in terms of mass. We can do that in terms of kilograms. We can do mass in terms of U. We can do mass in terms of MeV per C squared, mega electron volts per the speed of light squared. Now remember, this one is useful for energy in joules. This one is useful for energy in electron volts. And U is just kind of useful because it's less annoying numbers to add and subtract. It doesn't, or at least we don't have the conversions to do energy based on this U number. So you'll always be given these U's and you have to convert to one or the other. My strong recommendation, you start with U and you convert it to MeV per C squared. That is typically what AP will use because, right, we just like this number 18.1. It's a much nicer number to deal with than something times 10 to the minus 29, like the kilograms was. All right, I've got one practice problem for us here. This is a publicly available question straight from AP. So let's take a look at this one. We've got an isolated neutral lambda particle. A lambda particle, it's just something, if you looked at our standard model last time, a lambda particle is made up out of a couple of quarks. You don't have to know it. In a question like this, AP will always just give it to you. So isolated neutral lambda particle moving to the right with a speed of v. It then decays to a proton and a pion. The following are the masses of the three particles. How much energy is released when, and this should be a to the u. I don't really know why this and this are different. They should be the same. That's just a typo from AP. How much energy is released when that lambda particle decays? Okay, well, we start with this much, right? We start here with our lambda particle, and then we end with the proton and the pion together. We end with that. So if we take a look at how much we end with by adding these up together, 938.3 plus 139.6, we end with 1077.9 MeV per C squared. Okay, but we started with 1,115, and we end with 1,077. So where does that mass go? So we have 1115.7 minus 1077.9. Plug that into your calculator. 0.7 minus that, 37.8 MeV per C squared. So this much mass is just unaccounted for. We just don't know where that mass is, except now we do, right? Because we have Einstein's equation, E equals mc squared. And by the way, if you look at your equation sheet all the way down to the bottom, modern physics, E equals mc squared, there it is. So we have this this equation E equals mc squared. So mass 37.8 MeV per C squared. So mass times speed of light squared. Guess what we get to do? Cancel those out, top and bottom. So we just end with 37.8 mega electron volts. Answer D. Okay. I'm hoping that you are just as excited as I am by this, because this means, right, the most famous equation in maybe all of physics, E equals mc squared, you know what it's used for. You can apply it to all these different situations now, and that's just kind of awesome. You're to the point in this physics career of yours where you know how to use the most simple but most elegant equation that has maybe ever come into existence as far as physics goes, specifically or especially in the last 150 years or so, at least. Um, but this guiding principle is what allows us to get energy when we have fusion and fission. So nuclear fission reactors, it's because we end with less matter than we start with, because that matter's been turned into energy. Nuclear fusion, we end with less matter or less mass than we started with, because that matter's been turned into energy. We'll take a look further at all these applications for you start with energy and you can end with matter, which is kind of cool. So we'll look at that more in the future. But E equals mc squared, once again, this is called mass energy equivalence. So this mass energy equivalence, you now know how to use these terms right here. You know how to use that equation. Congratulations. I think you call yourselves real physicists now. All right, that's it for this video. See you next time.